I say tough with them. And anyways, but I look at this picture here, so you can see some people standing in here. So I just looked at this thing. I saw the side slopes are about one horizontal for one vertical. Looks like the bottom width is about 7 feet. And we got another indication how much water is supposed to come down this aqueduct here. And so there's some interesting pictures. Now, as you I might have mentioned, the aqueduct comes from the Eastern Sierra. It actually starts up in Long Valley, comes down, and they actually use the Owens River to get it all the way down through the Owens Valley into Lone Pine, and then they have to use pipes. Owens Lake is kind of a sink. It's kind of a low spot in the area, and there's really no outflow for it. So that they divert the water out of the area and somehow manage to get it by digging and using pipes and stuff like that. They got it out of where Owens Lake is and flowing on down towards Mojave and into the west side of Palmdale. Then they dug a tunnel under the mountains to and use pipes and stuff like that the rest of the way. The Los Angeles Aqueduct actually ends in right up at the end of Balboa. If you've ever been up, drive up to the end of Balboa, you can see where the aqueduct comes out. Here's a picture of it, and used to have a big sign there along Foothill Boulevard, which was the US 99 at one time. As a matter of fact, this picture is actually, it's got the new aqueduct and the old aqueduct. Let me see if I can get a better close-up of that. They built a second aqueduct in the 1960s, but this is the first aqueduct here that was built, and it comes right down. There's a spillway coming down as it runs into Van Norman Reservoir. Right up at the end of Balboa in 1913, they had about 40,000 people show up, or 30,000 people. It's a huge number of people. It was about 15% of the population of Los Angeles drove up on a dirt road called Balboa Boulevard and all the way up to the end of it to watch the gates opened up and watch the water come spilling. You can barely see the front of the water coming down the spillway here. And William Mulholland gave the big speech. He says, "There it is, take it," and he sat down. And so, but he was considered a genius for being able to bring this water in. It doesn't have a single pumping station. It's all gravity flow, the entire 260 some miles. And it's all done by gravity. It was built on schedule and under budget, so it was a pretty good accomplishment. So, but anyway, so that's it. Now, part of the problem of getting the water down from the Owens Valley is you don't always have you had canyons you had to cross. And you don't want to give up your hydraulic grade. You don't want to go down steep canyons and then no place to go to get it back up the other side of the canyon. So on those particular areas, they used pipes. And if you take a look at this picture here, they call this the inverted siphon. And this, when you drive up the Highway 14 north of Mojave, there's a place called Jawbone Canyon, and if you look to the west of Jawbone Canyon, you see this pipe coming down, going up the other side, and so it's about a 700-foot drop. So that means that the bottom of, and then they go back up the other side, and then continue in the ditches that are carved out in the side of the mountains there. But they don't want to drop this 700 feet, and then they got no way to get the water back up to their side, so they use a pipe to do that. And if a 700-foot drop, it's about 350 psi, and so it's a significant amount of pressure in the pipe at the bottom of these canyons. And so they actually had at the bottom sections, they had to have really thick walled piping in order to get it strong enough to able to hold that. And so one of the interesting stories about that Oh, you can see the size of the pipe here. It's about a 10-foot diameter pipe. And again, there's it going down Jawbone, and so it's quite a deal to build these things. But in order to get the pipes up to the site, this was around 1910. They were constructing this thing. They didn't have the biggest of cranes or equipment, so the pipes were manufactured back east, forged and shipped out on rail, and then they had to get them from the rail station. They had to get them up to the canyons where they're going to be installed. And so they used, where's that picture here? It's a really good picture. They had to use mules to get it up there. And this picture shows a 50, oh no, not again. Trying to get in here. Hang on.
It's still there. It's the top.
Oh, yeah, it's still there for you. I lost it. Okay, here it is. So they use these, they have 52 mules here. And so they had this massive wagon, weighed about 4 tons, to carry a, I don't know, about a 10 ton or something like that. They say each mule can pull about 500 pounds. And so it took 52 of them to pull 26,000 pounds. And so that's 13 tons. I think it was 10 tons for the pipe and about 3 tons for the wagon. And so it was quite a job. It had to go to this train station, had to pull it about 5 miles up to the locations where it needed to go. So yeah, anyway, so that's a whole another story. That's a very famous picture of using getting mules to pull those things. So anyways, so it was quite a feat, and it brought a lot of water into Los Angeles. But it wasn't. It didn't come without its cost. They built a reservoir. They had several reservoirs along the route, and they built one up somewhat north of Magic Mountain in San Francisco Canyon. It was called the St. Francis Dam, and you may have heard about that. The dam failed in 1926, killed over 500 people. It was a huge disaster. It's still the second largest disaster in the state of California. Does anybody know what disaster caused more deaths in the state of California than the failure of the St. Francis Dam?
Northridge.
Yeah, it was an earthquake. Anybody know which earthquake it was?
Northridge?
No, well, not. No, it was San Francisco. Yeah, no, Northridge. There's only like 60 people died in that. I mean,
okay,
it was quiet. But in San Francisco, what happened was they had the earthquake, and that did whatever it did. It was a 7 point whatever, but it busted a lot of natural gas pipes, and it burned the city to the ground. And so it was the fires that caused all the problems, and so that was a bad part of that. If I Google St. Francis Dam, St. Francis disaster site. So, oh, what did I do? I put it in the wrong thing. I'll try it again. Oh, here it is. Yeah, so here's the 12 billion gallons. Here's the dam here. And the dam failed. And this is what it looked like after the failure. Oh, yeah. This picture here. Can you see this picture? This one section of the dam stood after the whole thing collapsed. They called this the tombstone. It was a couple 100 feet tall. And yeah, it was at 12 billion gallons of water. And a few hours later, it had no water behind it. So, and it all went down into the Santa Clara River. It caused most of the fatalities were in the city of Santa Paula. They actually had about a 2-hour warning. It's several miles downstream. The water doesn't go that fast, and so they actually had some warning. And the police were going through the streets in the middle of the night on a Saturday night, in the month of March. It said, "Head for high ground. The flood's coming." And everybody looked outside. They could see stars outside. They said, "Oh, what are they talking about?" Nobody believed them, and so a lot of people were caught unprepared from the flood. And anyway, so yeah, it was a huge disaster. So Mulholland, he took the rap for it. He took all the blame for it. They gave him the blame. He accepted the blame, and he went into after the inquest and investigations were done. He went into seclusion after that. But Mulholland was a very powerful person in Los Angeles. They offered him the job. They said, "You're so popular." This was in like 1920. "You're so popular, you could be the next mayor of the city." And he said, "I'd rather give birth to a porcupine backwards than be mayor of this city." So that was his opinion. And anyway, so I have a sample problem to just kind of practice for this particular. I can find it here. Hang on. It's I put it here in the canvas, and so it's this one. I don't know if you guys will be able to see it. Can you see this thing called 493 final exam?
Yeah.
You can see that? Okay. Well, it was on the final exam, but this problem could have been on the first test because I gave him a problem to calculate the normal flow depth. And so anyways, so it all based upon this sign that used to be up there. I don't know if it's Granada Hills or Sylmar, but it's where the spillway is. This sign was here many years ago. Terminus of the Los Angeles Aqueduct, length 233 miles, capacity 260 million gallons daily. So I gave you a problem. This is what it said. Years ago, there was a sign at the end of Balboa where the Los Angeles Aqueduct enters Los Angeles. It claimed that the flow was 260 million gallons a day. If the bottom width of the concrete line trapezoidal channel is 7 feet, the side slope is 1.0, and the channel slope is 0.001. Now, I don't know if this is true or not. This is about as low of a number as you can see. This is like 5 feet of drop for every mile. So this is a very shallow flow. And I did look at some elevations and measured some lengths and stuff like that, whereas as the aqueduct winds through the to the Antelope Valley. And it seems a reasonable number. So I think this is a pretty decent number. But it doesn't matter what it is. It's just, can you calculate the same answer I calculated? So how deep would you build the aqueduct? I said, your results should be justified to an accuracy within 0.1 feet. Justify your design calculations. So you got to think, how would you calculate the normal flow? I gave you the discharge Q, and I gave you the slope, and I gave you the bottom width, and I gave you the side slope. And so how would you do it? Well, you got to make a couple of decisions here. Number one is, what is the Manning roughness factor? So that's one of the things you had to do. You had to go figure out what the Manning roughness factor is. So I chose a value of 0.15. You go into table 3.1, and it says for concrete, it says 0.013 to 0.015. So I use 0.015. That's the high end of the friction. So this is going to be the higher the Manning roughness factor, the deeper the depth. So so I use the high end because the question it really was based upon how, if you had this kind of discharge, 260 million gallons a day, how deep would you build your aqueduct with this bottom width, this side slope, and this channel slope? And so that was the question. And so I used the 0.015 at the high end. And of course, you work out the number and whatever comes out. Then you got to add a little bit extra height. You always put a little bit extra margin. They call it freeboard. You got to put a little extra on that to account for uncertainties and things. But yeah, so I chose a friction factor based upon this. So I went in table 3.1, found not the friction factor, but the Manning roughness factor, and I found that. Now, this discharge needs to be in cubic feet per second. So that's what this number is, 260 million gallons a day, divided by, there's 7.48 gallons in a cubic foot, divided by 24 times 3,600 seconds. That's how many, that's about 84,000 seconds in a day or something like that. And so you work all that out, it actually comes out 402 cubic feet per second. That's a lot of water coming down. And so, so that's where that number works out. Then of course the K sub n is just it's 1.49 cubic, I'm sorry, foot to the 1/3 power per second. The S0 is 0.0001. You got to take the square root of that, and that's 0.01. And then the bottom width is 7 feet, and you got to take that to the 8/3 power. Because what I'm going to do, by the way, this, I forgot to write the number down. It's figure 3.4. This should be figure 3.4 is where you have that chart showing for trapezoidal channels, you have like 4 different curves at 4 different side slopes, and there's one curve that says for a rectangular channel where the slope is actually 0, and so so that would be the rectangular channel. So it's like 5 different curves on there, and the first thing you had to do on the x-axis, you had to calculate this parameter. And then on the y-axis, you had this parameter, y sub n, which is the depth for normal flow divided by b. Okay, so I was going to use this to put me in the ballpark of where I need to be, because otherwise it's an iterative solution, and it's nice to have a good place to start. So b is 7 feet, that's in the problem statement. S0 is 0.0001, K sub n, it's 1.49, because it's either 1.0 if you're doing metric, 1.49 if you're doing English. The Q, you have to put in cubic feet per second, and then you have to choose the value of the roughness factor that you thought was appropriate, and explain your reasons. So I worked it all out, and so this value that goes on the x-axis of this chart, you remember the chart, it looks something like this. The chart looked something like this. So it had, and it was a log plot, but it had this family of curves for different things. And then there was one more curve that was for m equals 0. So this was m equals 0, 1, 2, 3, 4. And this was the value y over b, y sub n over b. And then this value down here was this thing here. So yeah, and so there was a log plot, so you have to kind of interpolate sort of logarithmically. And so I had this value on the x-axis 2.26, and so I came up wherever that was, went to the side slope of 1, came over here, and the best I could read was a value of about 1.25 based upon side slope of 1. And that gave me my first guess for y sub n is going to be, because y sub n equals this, y sub n over b equals this. So I just take 1.25 times b, which is 7 feet, and it came out 8.75 feet of height. Okay, so the question is, but is this accurate to within 0.1 feet? And you don't know. I mean, I got 3 figures of accuracy, but that doesn't mean anything. It all depends how well you can interpolate off of a chart. And so I don't know. So in order to verify if it's accurate, then I went into the Manning formula. Now the Manning formula, we already been through this part. This was in last class notes. They separated the Manning formula. They put all the known factors on the right hand side, and all the geometry factors involving the y sub n was equal to a times r to the 2/3. So this is the numerator is, well, R is just A over the wetted perimeter. So it's the numerator's area to the 5/3, the denominator is the wetted perimeter to the 2/3. So the question is, I have a value for Y sub n, 8.75. Here. Now this side here, I calculated is 405. And when I plug in the value of 8.75 feet, I get, on the left-hand side, I get 367.02. Okay, so it's not quite there. It's off a bit. And I don't know, and you don't know how far off it is till you get a second data point. So at this point in time, I just took a guess. I said, well, this was 8.75. Let me try 9.0. I don't know if this is too high, or this is still too low, or this is going to be spot on. I don't know. But if I want to have a second point, then I can kind of tell how far off I am. So the same formulation here, A times R to the 2/3, which is this formula here. So it's wetted perimeter to the, I'm sorry, this is the area. This is the wetted perimeter. And so I plug in these numbers and it comes out 388.8. So I went from 367 to 388.8, but I'm still short of the 405. So I got to go even higher. But what I'm going to do at this time, I'm going to extrapolate. So I'm going to extrapolate a new value for Y sub n based upon a target value of this right-hand side term being 405. Now the 8.75 here gave these values. They're the same values, but the 8.75 gave those values. And then the 9.0 gave this value. So, I'm just it'd be interpolating if I had the 8.75 and 9.0 bounded it on either side, but it didn't. It's actually extrapolating. So based upon that, I get a Y sub n of 9.19 feet. Okay, is that accurate? I still don't know how accurate that is, because maybe, the interpolation was kind of far off or whatever. So what I did is I took the 9.19 and I plug it back into this formula, and I get 406.2. Now, normally you would think, oh, that's pretty close, but I don't know how close. I just don't know. So, because I don't know, unless you do this a lot, you don't have a real sensitivity for how these things can change. And so, so I said, well, that's 9.19 feet. What if it was 9.18 feet? So I just tried a slightly lower number here, and it came out 405.2. Almost got it on right there. So this 9.18 is fairly close to what the value should be. It might be 9.179 or whatever. It could be. I could still get a little bit more accurate, but I'm only wanted to get it accurate within 1/10 of a foot. So if this is close enough, that means I wanted an answer between 9.08 and 9.28. So that's how I did that problem. Any questions on that?
All good.
Yeah. Well, that's the thing. You don't really, this is kind of new calculations for you. It takes a little bit of time to get a feel for these kind of numbers, particularly with something like this. Well, since you got Y's in the numerator, Y in the denominator and stuff like that, it's a little bit complicated formula. So you got, number one, you got to be real careful about your math calculations. And number two is you have to execute the formulas correctly. So yeah, so I calculated 9.18. But anything between 9.08 and 9.28 would have been a sufficient answer. Now, I might have also asked, is this a subcritical critical or supercritical flow. So how do you determine that? Well, one way obviously is to calculate the Froude number, but the Froude number might be a bit of work to try and calculate. What I decided to do is I was going to use figure 2-1, and because figure 2-1 is a plot that shows what the critical depth is based upon a variety of parameters. And so that's what I did. So figure 2.1, and it was a figure that, you put this, I got this crazy parameter along the x-axis, and then you read up the y-axis and you get y over b or something like that. So trying to look for it here. Yeah, so figure 2.1, I don't know if you can see it, it's this one right here. But again, it has this parameter down in the on the x-axis, and then you calculate this term over here on the y-axis, m y sub c over b. So but if you know all those other terms, you can use that. And I got a value that the y sub c had. If it was critical flow, then at that discharge, it would have to be 3.8 feet deep. Any questions about that part? Yeah, like I said, the question was, I asked this little supplemental question, is this critical? And there's a couple of different ways you can do that. And so you want to always trying to find, well, I was going to say find the easy way, but maybe you don't want to say that. But the way that you will generate the least amount of probability of error. And so on this particular one, it was a matter of just looking on that chart, figure out what the critical depth was. And if I'm nowhere close, then I would know if I'm supercritical or whatever. So I calculated 3.8 feet would be enough for critical flow. And so that would be a lot of people working on those calculations still. So it would be, and so it came out, I mean, we're talking 9.18 feet, and 3.8 is critical depth. So, yeah. Okay.
Professor?
Yes.
I actually had a question about I think I might have missed one when you brought up the 405. I'm not really sure where you got that from.
The 405 cubic feet a second?
Yeah.
Yeah. Well, in this Manning formula, Q has to be, well, it either has to be in cubic meters per second, and if that's the case, N is going to be different, and the case of N is different. But in English units, 260 million gallons a day in 260 million gallons a day seems like a lot, but it comes out to 402.3 cubic feet per second. So yeah, I don't know why it was why they would come up with that, but it was wait, so I'm sorry, what was the question again? Oh yeah, so why come up with this number? Yeah, so you don't have a feel for it, but it just takes a while. So it's just a matter, since I'm using English units, Q has to be in cubic feet a second, and so and I have gallons a day. Well, gallons is a volume, cubic feet is a volume, day is time, a second is time. So it'd be real easy to convert. So I 1 foot over 7.48 gallons. This is the number of conversion factor you should know in this class. And then 24 times 3600 is the number of seconds in a day. And so, so yeah, so then everything comes back to feet per second, and it can be, the rest can be calculated. Okay, so does that answer that question then?
Yeah, so you basically just rounded the 402.3 to 405?
No. I'm sorry. The 402.3 is the Q. This Q is the discharge. Oh, okay. Oh, that's right. You asked where the 405 came from. Okay, that was from this relationship. Remember, the Manning formula is a formula that looks like this. The Manning formula says Q equals K sub n times A times R to the 2/3 times S0 to the 1/2 I'm sorry. Yeah, to the square root of S0. Okay. And then divided by N K sub n. Okay, so that's the Manning formula. So if I rearrange the terms, I put everything that's based upon the depth, the flow depth, which would be the A and the R. I put all that on the left-hand side, and on the right-hand side, I put all these known parameters. And so once I did that, I just keep adjusting the value of Y sub n until the left-hand side is equal to the right-hand side. For this particular problem, these 4 parameters never change. Because N, we took the value that gave the deepest depth. So the higher the N, the deeper the depth. The Q was given to us, K sub n was given to us, and I was just going to say, what was I going to say here? I lost my train of thought. Yeah, if I calculate all these known parameters, then I adjust the value of Y sub n till the left-hand side is going to be the right-hand side. And the right-hand side, the product of all these values came out to be 405. So the N, 0.015, this is 402.3. And then we had the square root of 0.0001, which is the channel slope, is 0.01. And then 1.49 was this factor here. So all these terms is here. And you can see, 0.015 divided by 0.01 is 1.5. So these 2 terms here is 1.5. And then I divide by 1.49. So yeah, so 1.5 divided by 1.49. Yeah, this is going to go up just a little bit. So that's where the 405 came from.
Okay, yeah, I see.
Yeah, 405. It's close to what the discharge was, but that's because that was based upon this value of N that we used. If I had to use, well, I could have used N at 0.0149, and then of course it would have been. This would have been the 402 would have been the number of this right-hand side term instead of 405. But you can see, at least you can look at these things and say, yeah, 405 seems reasonable because it's got to be slightly bigger than Q. All these numbers, it's 1.5 divided by 1.49. That's, so we can see that, get an idea about how accurate our checks are. Okay, so anyway, so that's how where that 405 came from. So this is the target value that we want, and we just keep tweaking the. Well, you could do it. You could tweak the value of Y sub n till you get there, but we try to speed it up. We used the chart. We got 8.75. Well, it wasn't accurate enough, so we tried 9.0. Got a number here, and it was closer. And so then we extrapolated to get the 9.18. Okay. So there's a number of ways. If you just put this formula, you can just put this whole formula here in a spread. Where's my mouse? You can put this whole formula here in a spreadsheet, and then you just tweak the values of Y sub n until it comes out equal to 405. Okay.
Professor, what about y sub n over b equals 1.25? Where does the 1.25 come from?
Oh, well, that came from the chart. Let me go back to a previous set of notes. Let me just exit out of this thing here. Okay, so remember these numbers here. The I'm sorry. What? Okay, repeat your question again. I think I misunderstood it. Repeat your question.
The y sub n over b?
Oh, here, up here. Yeah, the y sub n over b. Okay, so at first we said we use figure 3.4 to get try and estimate a good value for y sub n. It's a chart, and we used that chart in an example yesterday that we calculate this parameter that goes on the x-axis. Remember this b to the 8/3 and all that kind of good stuff. If we look at this lesson from yesterday, so that would have been chapter 3. So you can still see these notes, right? You can see my notes from chapter 3.
We can see them.
Yep.
So we had this chart. It was this chart. This was figure 3.4. And this was for how to estimate the normal flow depth for a trapezoidal channel. So you calculate this parameter. There's the b to the 8/3 and all this thing. You calculate that thing, and then you find the appropriate. You find the appropriate curve here. When we're using an m equal to 1, so that's this one here. And so on the x-axis, the parameter we had was 2 point. I can't remember. It was 2 point something. Oh,
2.26.
2.26. So here's 2.2. Here's 3. 2.3 is roughly halfway between. The 2.26 would have been a value right there. And you come up to the m equals 1. And then you come over here and you come across this way. And I got 1.25. I mean, it's hard to read. About halfway between the 1 and the 2 is about 1.3, but you know, but you can sort of eyeball. You have to kind of put a logarithmic scale on there, because between 1 and 2, the halfway, or quote unquote half the distance, is 1.3. So yeah, it would be that. Okay, so that's what we did. So we get the y sub n over b. And then we can use that to get an estimate as to what the flow depth really must be. So.
Thank you. I have one more question.
Okay.
For the Manning factor, was there a specific reason why you picked the higher number rather than the lower number?
Well, the higher the number, the higher the flow depth. Because you think of the higher the number, it's going to mean you're going to slow the water flow down because you have more drag. So if you slow it down, flows at a slower velocity, then the depth has to go higher. So it was just all done to try and sort of calculate something on the high side of the depth so that I could calculate a conservative calculation. If I want to be aggressive about it and try to minimize funds to spend on this, I might have used the 0.013 and say, oh yeah, okay. And so, you know, but it's all kind of smoke and mirrors. You could just pick the best number you can.
You said you try to minimize the funds?
Well, you use the, yeah, if you want to sort of get your best ballpark number, you might want to, you know, you're not going to have to build such a deep channel. You use 0.013. That's going to be a slightly lower channel height, and so you might get get aggressive on your proposal. But a lot of times people like to put cushions and all this stuff, using the higher end, yeah, it's It means you're going to get a higher number. It means you're going to have more expenses associated with it. But what's the right number? Probably the one in between, in the middle. Goldilocks, like Baby Bear's porridge, because it was somewhere between hot and cold, and it was just right. So that's my rule. They all comes out. The law of averages works almost every time. So yeah, so that's what you. But there's a range, and so it depends if you want to be. You make sure you want to make sure you don't build this thing too tall. I mean, you want to make sure you don't build it tall enough. You don't want that to happen. So erring a little bit on the high side would be okay to do. All right, does that help?
Perfect. Thank you.
Okay. So anyway, so are there any questions about that particular sample problem?
Is KN always like 1.0 if it's meters and 1.49 if it's
Right, yeah,
Okay.
K sub n, you read in the textbook, and it's just it's a factor. Notice that in this formulation here, it's a factor to make sure that, well, in this particular case, the K sub n is a factor to make sure that, well, let's back up to the Manning formula. If you look in the Manning formula, A times R to the 2/3. Well, R is the, of course, is the hydraulic radius, and R is the area divided by the wetted perimeter. So that's why in the numerator here, this is the formula for the area to the 5/3, and the denominator is the formula for the wetted perimeter, and that's to the 2/3 power. And so, so you come over here. So these units here, if you look at them, you have area is in units of feet squared, and R is in the units of feet. So altogether, you have units of feet to the 5/3. You got to have, so this is in units of feet to the 5/3, or it might be meters to the 5/3 or whatever. So this side has to have the same units. And so if you look at the units here, where did why don't I have the units? Oh, I did up here. Okay, so I put all the units here. So, so we had, this is a non-dimensional number. This comes out in cubic feet per second. Now, so this is cubic feet per second. And then, and so, so the numerator has cubic feet. And then you look down here in the denominator, and we got feet to the 2.2 2/3 power. This is feet to the 2 2/3 power. So this has to have a unit of feet to the 1/3. For this Manning formula to work, this K sub n has to have a unit in here of feet to the 1/3. So this is going to be feet to the 1/3. This is feet to the 8/3. So you multiply those together, you got feet to the 9/3, or feet cubed. And that cancels the feet cubed in the numerator. And then of course you got 1/seconds here, and the numerator you got 1/seconds by the time they're done. So that's where that number comes from. So that's just a number to make the units work out when you think about it. But if you do it in English units, it's got to be 1.49. And if you do it in metric units, it's 1.0. So the whole thing with the Manning roughness factor and all these other things was all based upon you working for metric unit. So that's why it came out a little bit different. I mean, the units would be meters to the 1/3 per second, but the numerical value is different. And of course, it turns out that 1.49 cubed is 3.28, and there's 3.28 feet in a meter. So this 1.49 just didn't come out of nowhere. It's really the cube root of the conversion factor from feet to meters. And so, or meters to feet, whichever way you're looking at it. And so that's why, because it's got to have units of feet to the 1/3. So this is actually 3.28 to the 1/3 power. So that's where that value came from. Any other questions about using the Manning formula?
Yeah, I have a question, Professor. So I got a bit lost on how you decided on which value to give the mining factor n. How do you decide it was 0.015?
Well, yeah, if you go to table 3.1, it has a list of Manning roughness factors to that you can use in the Manning formula. So table 3.1, it's on page 74 of the book. So it says called the Manning roughness factor. For concrete, it says the Manning roughness factor N is 0.13 to 0.15. If I had something like, what if I had something like asphalt? Well, that's a 0.16 to 0.18. So it would be rougher, certainly, if it was asphalt. But concrete came out 0.13 to 0.15. And as I said, the 0.15 gives a higher normal depth than 0.13 because it's generating more. It means you got more drag. So the water, the flow rate slows down a little bit. So that's going to give you the largest depth.
Okay.
That's why I chose it.
You said table 3.1, right?
That was table 3.1. Yeah, there's concrete, grouted riprap, soil cement, asphalt, bare soil, rock cut, fiberglass moving, woven paper net, jute net, synthetic mat. So there's all kinds of different, and they all got a little bit of a range to them. So yeah, so that's what you get.
Thank you.
Okay. All right. Any other questions about the Manning formula? So the Manning formula is pretty good. It's just that, you know, it's if for something like a trapezoidal channel, there's an iteration involved, and so if you can put this into a spreadsheet, it becomes easy to work with. But it does take some iterations, and you just want to be careful to do it so you don't make numerical mistakes. And so, because taking numbers to the 5/3 is not something that you maybe have a great deal of feel for what those values should be. But yeah, so anyway, so that's where those values came from. All right. Any other questions about this particular problem? All right. So as you can see, now you look at that channel that those people are it looks like it's going to be deeper than 9.2 feet. But again, I said when they actually build these things, they may add a little bit of extra height to it. There's a formula for that we'll talk about in chapter 5. So maybe the channel height is around 10 feet or something like that. But and you know, can't tell exactly if that's a 10-foot channel. But then again, maybe the channel slope wasn't 0.0001. It might have been something different. So we don't really know. But I did kind of check that number, and it seems reasonable for what we have. All right. Okay, well, that's really all I have for today. You got some homework problems that you're going to have for the next week on this. What I'll do is I'll get the solutions posted on the Canvas site there for chapter 2 problems. I'll get those posted this evening, and we'll be able to you'll be able to check your work against those things. And then I'll have the video put on the My CSUN box, so you can always use that to try and reinforce your learning experience. All right. Okay. Then with that, why don't we just call it an evening, and then we'll meet again on Tuesday and pick it up from there.